I want to work on or show a few problems where we use percentages to find values. Going to hide this ribbon up here so we get it out of the way. So the last video I made, we talked about how we could find a value using percentages. So there's numerous applications in the real world, and here we're going to see examples in the medical field, in architecture and design, and tire manufacturing. So in each problem, I'm going to go through the following steps: identify the mean, identify the standard deviation, identify the probability equation, use the normal calculator and StatCrunch to locate the value or values, and interpret the results in context. So this first one's kind of near and dear to my heart right now because my daughter-in-law is 5 months pregnant with a baby boy that my grandson. So I guess especially in light of what's going on with the global pandemic, we're watching these days very carefully. So here's the question. The lengths of pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. If we stipulate that a baby is premature if the length of pregnancy is in the lowest 4%, find the length that separates premature babies from those who are not premature. Premature babies often require special care, and the results could be helpful to hospital administrators in planning for special care. So I've used highlighting function in Word, and you notice I found the mean right here of 268, and really I should put days there. And same for here, the standard deviation, which is in, I'm sorry, whatever color that is, in days here. And here we find our probability equation that x equals question mark equals 0.04%. So I'm going to go ahead and go to StatCrunch and use the normal calculator here. I'm just going to write down 2 pieces of information. So when I open up StatCrunch, I'm going to go to the normal calculator. My mean was 268. My standard deviation was 15. And the bottom 4%. So I want everything to the left of 0.04 as a probability, and that gives me 241.7 days it would round to. I'm not going to go ahead and work through the other ones like I did in the other videos because we've been working with the normal calculator for a while, and I've already put the displays in each one of the questions. So I'm going to go ahead and back to the document. You see that to the left, this is shaded. So what is the interpretation here? The length of the pregnancy that separates the lowest 4% of babies born is approximately 241.7 days. Babies born prior to 241.7 days will often need special care. Well, here's a real-life application. Now, the next one is, I come from a family of contractors, and they build things, and so there are standard heights to doorways, and tell you the truth, I don't know what that is right now. But when we build things, and if anybody has gone back, for example, and seen the Mayan ruins, you'll see doorways that are really much shorter than what we see here. So apparently, the prediction is that, or the interpretation is that people weren't very tall there. So anyway, men's heights are normally distributed with a mean of 70.2 inches and a standard deviation of 2.8 inches. If a statistician designs a house so that all doorways have heights that are sufficient for all men except the tallest 5%, what doorway height would be used? So again, we found our mean. Apparently I didn't do a very good job. Well, I think you can get the picture here. The mean equals 70.2. The standard deviation is 2.8. The probability of next. Now, notice what I did here. I like working to the left, and there's other ways we could have done this, but I'm going to go ahead and put it in this way of 100 minus 5% equals 95%. And here we see 70.2 for a mean, 2.8 the probability of 0.95, and I get a door height of 74.8. Interpretation: the height that separates the tallest 5% of men from the bottom 95% of men is approximately 74.8 inches. The doorway height must be taller than 74.8 inches. I want to pull StatCrunch back up for just a minute. Well, actually, I did that too soon. I need to write down I'm going to pull the document back up first, and that was 70.2 and 2.8. So when I pull StatCrunch up, 70.2 will go right here, 2.8. Now I can change this to a greater than sign and put 0.0. And if you'll notice, I can work to the right if I wanted to. So I could put that 5% in, change my inequality sign, and you'll notice I still get 74.8 inches. So, it's kind of a quirk of mine that I prefer to work to the left, but either way will work. Where students get themselves in trouble is they zig when they should zag. So I guess why I probably try to work to the left is I figure I'm less likely to make a mistake, but I still make plenty. So anyway, that's let's go to our last example, and that is tires. So the lifetime of a certain type of automobile tire in thousands of miles is normally distributed with a mean of 40 and a standard deviation of 5. The tire company wants to guarantee that its tires will last at least a certain number of miles. What number of miles in thousands should the company guarantee so that only 2% of the tires violate the guarantee? I probably need to rewrite my interpretation here because what they want us to say here is the guarantee the guarantee should be for 29,730 miles. Now, nobody would do it that way. They might make it for 29,000 miles. They probably make it for 30,000 miles. But, when you're dealing, if you're a business that's dealing with thousands and thousands and thousands and thousands of tires, that those small percentages can get to be really big numbers. But anyway, the guarantee should be for 29,730 miles. So let's go back. I went ahead and multiplied everything out. So it says 40, and these are in thousands of miles, so that's 40,000. The standard deviation is 5,000 miles, and the probability that X equals 0.02. So if we go down here, you see I put 40,000 for the mean, 5,000 for the standard deviation. I put the O2 here. Again, we're working to the left. These are the ones that would violate a guarantee of 29,730 miles. Now, I do want to show you, though, I went ahead and did this. What if I didn't multiply it out? What if I used the 40 and the 5 that's given in the problem? Notice I still get 29.73, and if I multiply this by 1,000, you notice either way I get the same result, which is what we would expect. Those are 3 applications. These are kind of like things you will see on the exam, and some applications of how you might use them in the real world. This is the last video I'm going to make this semester for the normal distribution. I should have probably cleaned it up a little bit because I know I kind of was bouncing around there at the end, but in an interest of time, this is what we're getting. So good luck.